Hello, and welcome to lecture 34 on calculus with parametric curves. So in our last lecture, we looked at what a parametric curve is, and in this lecture, we aim to do lots of calculus things with these parametric curves. So we're going to find the slope of these curves, we'll do the tangent line to the curve, find where the tangent line is horizontal or vertical, we'll do concavity, we'll do arc length, so we're going to do just a lot of calculus stuff that we're used to from Calculus 1 on these curves. So in the previous lecture, we saw it's possible to rewrite parametric equations. So there were two equations just like this, x equals f of t and y equals g of t. And we could write it in the form y equals f of x, where we got rid of the parameter t entirely by doing some kind of substitution or something like that. So suppose that you're able to do that. Suppose we're in this situation like we were last time, where you can get rid of that t variable, and you can write the equation like this. So we can write it as y equals f of x. And then y is g of t, right? Y is a function of t. So that means that g of t is equal to capital F of, and then x is the parametric equation f of t. So that's another way of writing it. Now, let's take the derivative of both sides with respect to t here. So I have g prime of t equals, and then how do you find the derivative of this composition of functions? Well, from Calculus 1, we have the chain rule. So you do the derivative of the outside, which is capital F prime. And then we leave the inside alone. So this is lowercase f of t inside here. And then the chain rule part here is we do the derivative of the inside, which is little f prime of t. So then notice, as long as f prime of t is not 0, so we'll say f prime of t is not equal to 0, you can divide this to the other side. So this means we have g prime of t over f prime of t. That's equal to f prime of, and what was this f of t again? Well, that was x. So this is our formula we're going to be using for the derivative of some parametric curve. So we have this form. However, we can rewrite this. So this right here is our dy dx. We can rewrite the slope of the curve as the following. So what is g prime of t? Well, that's just dy dt. That's the derivative of this equation right here with respect to t. So this is going to be dy dt divided by, and then what is this f prime of t? Well, that's the derivative of x with respect to t. So this is dx dt. So this will be our derivative, the slope of the tangent line to this parametric curve. And we just have this formula as long as dx dt is not equal to 0. Otherwise, this would be undefined. So what the great thing about this formula is we can calculate the slope of the tangent line, and we can do that in a way where we don't need to eliminate a parameter or anything like that. We can just go ahead and calculate the derivative given two parametric curves. So let's do an example of this. We're going to find an equation of the tangent line to the curve x equals e to the root t, y equals t minus ln of t squared. And we're going to do it at the point t equals 1. So we're given two parametric equations, and we're trying to find the slope. Well, we're going to follow this formula. First thing I'm going to do is I'm going to use a log rule here. Just notice that this is equal to y is t minus, and if I bring that 2 in front, I get 2 ln of t, just using that log property where I can bring a power in front. All right, so let's calculate the slope first. We need the slope of the tangent line. So slope is equal to dy dx. And it's equal to dy dt over dx dt by our formula. So let's compute these separately. The first one is dy dt. So what's the derivative of y with respect to t? Well, the derivative of t is 1 minus, what's the derivative of ln? It's going to be 1 over t, but I have a 2 in front. So this will be 2 over t. And now we're going to compute the derivative of x with respect to t. So for the function e, all you do is you write e here. So I have derivative of e to anything is e to itself, so e to the square root of t. However, by the chain rule, I need the derivative of the power as well. So the derivative of the power is just 1 over 2 root t. And this is the complete derivative of x with respect to t. So what I need to do now is I need to plug in t equals 1, because that is the specific spot I'm looking at in the problem. So if you plug in 1 into this, I have a little bit of room up here to do that calculation. This is going to be equal to 1 minus 2 divided by, and then I have e to the first power times 1/2. So I have 1/2 e to the first power. And then from there, what I'm going to do is I'm going to simplify this a little bit. I get negative 1 over 2 times e. But then if you divide by 1/2, that's like flipping this up here to negative 2 over e. And this is the slope of our tangent line. Now, to do the equation of the tangent line, we need the slope. This is m. But also, we need an xy coordinate. So what I need to do is I need to plug in t equals 1 into the original equation, and then I can find the xy coordinate. So the original equation, first for x, if I plug in 1 for t, I get x and then e to the 1, which is e. That's my x coordinate. And if you plug in 1 for y, it looks like I get 1 minus ln of 1, which is 0. So 1 minus 0 is 1. So again, I just took t into the original equations for that. So that's my point. And I also have a slope here. So now I'm going to go ahead and write the equation using point-slope form. It's y minus y1, which is 1, equals m, the slope, negative 2 over e, times x minus x1 is e. So this right here is the equation of the tangent line to the curve. Now, I could rearrange that, I guess, and put it in a different form. I won't, but you could if the directions asked you to do that. But I'll just leave the answer right there. Now what I'd like to do is I'd like to find the points on the curve where the tangent line is either horizontal or vertical. And this time I'm going to work with this set of parametric equations right here. So when a tangent line is horizontal, this means that the slope is 0. And then when the tangent line is vertical, it means the slope is undefined. So we have two different goals here to find this one and to find this one. But to find either, the first thing you're going to have to do is you're going to need to get dx dt, and you're going to need to get dy dt, because they're part of the slope formula. So dx dt is negative 2t, and dy dt is going to be 3t squared minus 12. And now I'd like to build the formula for the slope. So the slope formula, dy dx, is dy dt over dx dt. And then what's that equal to? Well, dy dt is 3t squared minus 12. Dx dt is negative 2t. So that's the equation. This is the slope of my tangent line. So this is the slope of the tangent line to that curve right here, to this parametric curve. And now let's focus on horizontal first. So to find out where this is horizontal, I need this to equal 0, this entire fraction. So the only way you're going to do that is you're going to set the numerator equal to 0. That's how you get the fraction equal 0. And I should also warn you, and the denominator cannot be 0. So what we'll do now is we'll set the numerator equal to 0 in order to find where the tangent lines are horizontal. So here's our numerator. It's 3t squared minus 12 equals 0. So 3t squared is 12, or t squared is 4. So there's two possibilities. t could be plus or minus 2. And that's fine. It's in the domain of each of these original equations, so we can plug in either one. So we're going to convert this into xy coordinates. So what happens when t equals -2? What happens when t is 2? What original xy points are those? So go to the original. When t equals -2, if I plug in -2 here, I get 10 minus 4 is 6. And if you plug in -2 here, you get -8. And then minus, and this is going to be minus 24. So this is actually positive 16. And this is my x and y coordinate where we have a horizontal tangent line. And then here's another one. If I plug in positive 2, I get 6 again for x. And then here I get 8 minus 24 is negative 16. So these are the two spots where the original curve has horizontal tangent lines. And now we'll do the same thing for vertical. So for vertical, I would like the slope to be undefined. So I need to set the denominator equal to 0. And also, I need to be careful. And the numerator shouldn't be 0 at the same time. I'll address this in a moment, what happens when they're both equal to 0. I'll briefly talk about that. But let's first focus on this. So if I set the denominator equal to 0, that equation is just -2t is 0, so t must be 0. And then what xy point does that correspond to? Well, if you plug in 0 here, you get 10 for x. If you plug in 0 here, you get 0. So at the point 10, 0, you have a vertical tangent line. And I will make one statement right here. What happens if both of these are equal to 0? So suppose there is some t equal to a such that dy dx is 0 over 0. So suppose that there was a t value that did that. What would you do? Well, in this case, you would consider the limit as t goes to a of dy dt over dx dt. And in this case, it's 0 over 0, right? So you'd have this. And then you would use, what could I do to find this limit? What do we know from Calculus 1? It's L'Hopital's rule. Use L'Hopital's rule. So if you're ever in a situation where you see that you have a t value where both of them are 0, take the limit and use L'Hopital's rule. So that's a derivative of each of these. And then after that, reevaluate at a and see what you get. OK, so from here, we're going to look at a couple other applications of calculus to parametric curves. We're going to look at concavity, and we're also going to look at arc length. So I will see you for that in just a moment. Welcome back. So now we'll see the second derivative and also the arc length using parametric curves. So the second derivative, notated d squared y dx squared, has useful applications as well. Remember that it's the concavity of the graph that you're looking at. So what's our formula in this case? Well, the second derivative is the derivative, so d dx of the derivative, dy dx. So here we are taking the derivative of the first derivative. That's the second derivative. And it turns out that this is the derivative with respect to t of dy dx divided by dx dt. So we're talking about this in terms of the parametric equations that we're given, x equals f of t and y equals g of t. So we already know the formula for dy dx, so we'll simply take another derivative of that. We're also going to divide by dx dt. So we'll do an example right here that will illustrate this equation. So we're going to find the first derivative and the second derivative for the parametric equations x equals 2 sine t and y equals 3 cosine t on the specific interval from 0 to 2 pi for t. And then further, I want to know which values of t will this curve be concave up. So this is a question about the second derivative. All right, well, let's start basics. So we're going to find the first derivative. We're going to need it as well for the formula of the second derivative. So remember from the last part of this video dy dx is dy dt divided by dx dt, as long as dx dt is not 0. So then what's this? Well, I need to go to my equations and find out what dy dt and what dx dt are. So what is the derivative of y with respect to t? Well, we'll look at this equation right here, and it's negative 3 sine t. And then, what is the derivative of x with respect to t? Well, that's going to be 2 cosine of t. So the first derivative, if I just take my sine over cosine here, it's going to be negative 3 over 2 times tangent of t. And this is the first derivative of the parametric curves here. So now let's go ahead and develop the second derivative. So what I'm going to do now is I'm going to take the formula here. I have the second derivative is, and I'll take this right here, it's the derivative dy dt of, and I need to plug in the first derivative, which is dy dx. So I just found that right here. This is my dy dx. So this is going to be plugged in here. So I'm going to take the first derivative of negative 3/2 tangent of t over, and then I need the derivative with respect to t. But that's just right here. This is the 2 cosine of t. So I need to go ahead and finish this. So the derivative of tangent is secant squared. So I'm going to have the derivative of this is negative 3 over 2 secant squared t divided by 2 cosine of t. And then what is this? If I divide 3/2 by 2, I get 3 over 4. And then if I move all of these secants down here, the 2 secants down here, that's like having two more factors of cosine down here. So this is the same thing as 3 over 4 cosine cubed. So this is 3 over 4, and I have cosine cubed now in the denominator because I've moved these secants down here. So this is the second derivative. So we'll label this second derivative. And this right here, this is my first derivative. So now, how do I find something's concave upward? Well, I need what to be true about the second derivative. We need this second derivative right here that we just found has to be what type of number? It needs to be positive. So if we have the second derivative is positive, then we're going to be concave up. So the question is here, let me solve what t values do this. I'm going to multiply both sides by negative 4/3. So if you multiply both sides by negative 4/3, you get 1 over cosine cubed t. So this, imagine I'm doing this and multiplying both sides by negative 4 over 3. What does that do to the inequality over here? Well, if I multiply both sides by a negative, it flips the inequality. So now I have 1 over cosine cubed t is less than 0. When will that be true? Well, we need cosine of t, cosine cubed of t. This needs to be a negative number because I'll have a positive divided by a negative is less than 0. So what I need is I need cosine of t cubed to be less than 0. I need that to be a negative number for this to be true. Well, when is this true? This means I'm going to need cosine of t. That also has to be a negative number. Because if cosine of t was positive, you would cube a positive number and get a positive, right? So I need cosine of t, just one factor of it, to be negative. So when I cube it, it's still negative. So when is cosine of t going to be negative? We have to think of our unit circle on this interval right here. There are 2 quadrants where this is true. The first one is in quadrant 2. So when t is between pi over 2 and also pi, but then continuing on in the third quadrant as well, cosine is negative. So we need to go from 3 pi over 2, or sorry, pi over 2, all the way to 3 pi over 2, because that's the second and the third quadrant. So for this interval, we will be concave upward. Okay, so there's an example of finding the first derivative, and you use that to then build up the second derivative for a parametric curve. Okay, let's take a look at this last example. So before I do that, I'm going to introduce you to the formula for arc length. So you take the arc length formula we developed in the previous lecture, and you use our parametric equations here. You plug it into that formula, and now a new iteration of this formula is we take the integral from alpha to beta. So say we have some curve, and you're interested in finding the length of the curve from some alpha to beta for a t value. So then we suppose c is traversed exactly once, and then the arc length of c is going to be dx dt squared plus dy dt squared. And we find this by just taking the equation we have for dy dx, this one right here, and plugging this into our old arc length formula we had earlier. So that's the new one that we get in terms of this new situation for parametric equations. So this is the formula for arc length in this case. What I'd like to do now is I'd like to find the exact length of the curve of this parametric equation, these two parametric equations here, on the interval 0 to 1. So this is my alpha, and 1 is my beta. All right, so let's practice doing this. I'm going to need dx dt and dy dt. So dx dt, taking the derivative of x with respect to t gets me 6t. And then dy dt, that looks to me like 6t squared. So using these, I'm going to plug it into the formula. I have the length from 0 to 1. I'm going to take 6t and square it. So 6t squared. And then here, dy dt, I'm going to take 6t squared and square it, dt. So the length of the curve relies on me calculating this integral. Let's do one more step over here. I have the integral from 0 to 1. This is the square root of 36t squared plus 36t to the 4th dt. Let's go down here and continue. I'm going to do some factoring. So both terms here have 36t squared in common. So I'm going to write 36t squared, parenthesis. And if I factor that out of both of them, I get 1 plus t squared. And now I can take the square root of this factor here. So this is 0 to 1. Square root of 36 is 6. And the square root of t is going to be, a t squared is absolute t, but my t is always positive based on my bounds here, and here as well, the 0 to 1. So I'm just going to get 6t here. This is a radical 1 plus t squared. The way to handle this is I'm going to do a u sub. I'm going to say u is the 1 plus t squared, which means du, if you take this 2, bring it down, du is 2t dt. And I can divide both sides by 2 as well. So 1/2 du is t dt. So let's work on substituting into this right here. I have 6. Let's change my bounds of integration. So my old lower bound is 0. If you plug in 0 now for t, you get 1. And then similarly for the new upper bound, you had 1. If you plug it in here for t, you get 2 for the new upper bound. T dt, this right here, t dt, I'm going to replace that with 1/2 du. And then finally, 1 plus t squared is u, so I have the square root of u. In other words, I have u to the 1/2, which is a much nicer integral to take now. And I take this using the backwards power rule. And look, this is 3, right? 6 over 2 is just 3. So going backwards, I have u to the 3/2 times 2/3. But I have this 3 that's just sitting here as well as a constant. And I'm going to evaluate that from 2 to 1. Let's cancel these 3's just to get them out of our way. So we have 2. And then if you plug in 2, you have 2 to the 3/2 power minus 1 to the 3/2 power. It's just 1. 1 to any power is just 1, right? So here I get 2 to the 5/2 power, if I add the power 1 and 3/2 together, minus 2. And then what is this? Well, now I'm just getting a little picky with how I want to write the answer, huh? But this is 2 to the 4/2 power times 2 to the 1/2 power minus 2. But 2 to the second power is 4. And then this right here is just nothing more than root 2, right? So I'm happy with that. I'm going to leave it like that now. So that is the exact length of this curve using this newly formed arc length formula, where you can find the arc length of parametric curves given in this manner. So this is just a more convenient method for this situation to find the arc length. All right, thank you so much for watching. If you have any questions, as usual, please reach out to me by email, and I'll see you next time.